Good morning, welcome. Thank you all for coming. It's nice to see so many people here, and again, thanks for braving this kind of weather to get here. As was mentioned, I'm Wayne GROSZKO. I work in the Applied Energy Research Lab at the Nova Scotia Community College. And I'm going to speak a little bit today about the value of solar energy. We work a lot with solar energy in our lab, and I'll also extend my thank yous to the team that I work with, 12 amazing people who really have a passion and a high degree of competence for their work. So much appreciation there. Also, by way of acknowledgement, the work that I'm going to speak about is supported by many partners, and here are some of them. I realized on the way here that I'd forgotten at least one logo. I'm sure there are others. Solar Nova Scotia's logo hasn't got up there, but Solar Nova Scotia contributed to this work as well that I'm going to speak about. And we have quite a number of other partners on other projects as well. So the collaborative aspect of it is really, really a wonderful thing. So when we talk about solar energy in the context of a building, I'm going to use this really fantastic building as an example. Some of you will recognize this building. It's called Billiken House. It is a high-performance building that was constructed by Nova Scotia Community College as a kind of a teaching laboratory. So the students do experiments down in there. It's the Energy Sustainability Engineering Technology students, or ESET. Are any of those folks here today? There we go. ESET students and graduates. Great program. This house is amazing in various ways. It's built nearly, I say, to the passive house standard, which is what Laurie Rand is going to speak about a little bit later. It didn't quite make that, but it made at least the R2000 standard, and it's highly energy efficient. The walls are quite thick, well insulated, got triple glazed windows. And the reason that I like to use this house as an example is that it clearly illustrates all in one building three very valuable ways of using solar energy, all of which can be quantified. And they very simply are solar heating, solar water heating, and solar electricity. So they're all there on this building, and I'm going to talk a little bit about each of them. Solar heating, you can see that this is a winter day. That's my friend Caitlin in the foreground demonstrating winter clothing. There's snow on the ground. Also a sunny winter day. The temperature inside the house on this cold day in February was about 25 degrees Celsius. And the reason for that is the sunlight coming in the south-facing windows. So that's basically, many of you will be familiar with, passive solar home design. But what I'm basically going to show a great little experiment that the ESET students and faculty conduct each year using this house. In the middle of typically January or February, they pick a week and they turn off all the auxiliary heating systems in this house. Just turn the heat off. So imagine if you live in a house, what would it be like if you think of your own house, if you turned off the heat in the last week of January for the entire week? So what would it be like? What would happen in that house? Well, this is what happens in this house. So, finally some data, because it's the data conference. This is the outside temperature in blue on the bottom during the course of this 6-day period. And this was just last week. So this is kind of like hot off the presses data. And in the upper is the interior temperature in the main hallway, which is sort of an open space in the middle of the building. And what is interesting to see here is that, for example, last week we had this run of days. Now this is in Middleton, I should have said, Middleton, Nova Scotia in the Annapolis Valley, so the temperatures are a little bit colder typically than they are here. So we had a run when the average was minus 9.1 Celsius for 3 days straight. What happened to the indoor temperature of this building? It gradually fell, and to be expected, because obviously it's much colder outside than inside. Now, heat's not on, the power is still on, so there's a little bit of auxiliary loads, like the water heater might come on every now and then, maybe a few lights, but there's really not very much energy being used in this building to keep it warm. Essentially, it's the effectiveness of the insulation. So there's some interesting patterns you can glean from this data. If you take this night right here. Oh, the yellow dots are sunrise. So we'll talk about that in a minute. Every sunrise is marked with a yellow, diamond. So in between them, say here and here, you have times at night when there's essentially almost no heat being put into this building. So you can actually measure its decline in temperature with time due to straight heat loss, what's called the time constant. And we're proposing that that's another interesting way to characterize buildings for their energy efficiency, is calculate their time constant. So it's fairly easy to do that if you have willing volunteers who are willing to turn their heat off for a few days. Maybe that's not going to be so easy. But if you do that, and then in the nighttime you measure the drop in temperature very accurately, then you get a time constant for the building. And it's going to be different depending on how well insulated the buildings are. So for example, this night, the temperature dropped by 1.7 degrees Celsius during the night. That's really high performance for a building. If you, again, consider how most buildings would drop on, say, this night, a -9 night, how much the temperature would drop. And then how does solar energy come into this? Well, you see what happens after sunrise, especially this day, which was sunny. These days were quite cloudy, so you only see a little bump. Obviously, the sun starts pouring in those windows, especially on a sunny day, and heats it back up. So there was a rise of 6 degrees Celsius in the building just on sunshine alone. So you could go back in, I won't get into the details, but you could go back in and quantify how much solar energy is contributing directly to the heating of this building. The rest of the heat would be the heat from the occupants who live in it and all the appliances, and then the auxiliary heating system, which is off during this experiment. So that's interesting. And we're talking about values. Value is, what do we value? And this is one of the current first-year ESET students, Morgan Mason, standing inside Billiken House with the heat off. She's got her sweater on. It's probably not toasty in there, but you can get through a difficult situation where maybe your power's out or the heating's gone off. No pipes are going to freeze in this house. That alone, on the insurance of no pipes freezing in a house, you can't, under any foreseeable weather conditions, you can't freeze this house because every day some sunshine will come in and warm it up a little bit. So this one's more about the value of insulation, really. So I always love that they do that experiment every year, and it's good to see the numbers that come out of it. Okay, so moving on, hopefully. Solar water heating, the well-established technology. That is thermodynamics, 2-collector plate solar water heater. There have been many hundreds, probably over 1,000 of them installed in Nova Scotia. And we have one there. And what I'm going to talk about is data that we've been collecting in our lab for 5 years now through the HRM Solar City program. Some of you may be familiar with that, very successful, award-winning, municipally based financing program for solar water heaters. And now it's in a new phase, which I'll talk about in a minute, that's doing solar electricity as well. But when it started, it was only solar water heaters. And that was just over 5 years ago. And it was very successful in getting over 400, well, almost 400 of them to be installed. And of those, a very visionary decision was taken that many of them would have a data collection system on them, collecting a whole bunch of parameters on the performance of those systems once a minute and sending it to a database. Through various partners, including Thermodynamics, HRM, Dalhousie University, we have that database and we use it to do various kinds of analyses on hot water consumption, the effectiveness of solar water heaters. It's a tremendous resource. And I'll give you one example. Because these have been operating for 5 years now, it raises a really interesting question. What have they been doing? So how have they been performing? So we did some analysis on that and calculated the energy savings from each of the ones that we had in our record of over 200, and did that month by month. And this, I'll just caveat, this is marked preliminary because we haven't actually finished doing the analysis yet. In part, you see it ends towards the beginning of 2018. We're going to add 2018 to it very soon. And then, I don't know how many of you have worked with big data sets, but there's always issues around missing data, around numbers that are impossible, and how do you account for those. So we're still crunching through some of that. So this might change a little bit, but I think it's pretty close. So what do you see there? Each year, I mean, obviously the most obvious pattern, we've got time going on. Here's a year, and the energy savings on an average installation in kilowatt hours. And obviously it goes way up in summer. That's to be expected, no surprises here. Overall, and I haven't got this number up here, but we roughly estimate that this program on the whole has saved over 2,000 tons of CO2 emissions from being emitted to the atmosphere already. And I didn't put that number up there in print because, again, it's quite preliminary. But soon, we should be able to pin a number on what the savings from this program have been, and they're huge. But these are averages, what's up here. What's interesting to me is the average is one thing, but what about the variation? And when we look through the data set, some systems in there, some individual installations save much more than others. And so there's quite a large range, and the range is as important as the average. So, so what do you think might be some of the things that would affect? Meaning one household with a solar water heater would get more savings than another household. Well, obvious things. Maybe their solar panels are pointed a different direction. Maybe they're tilted a different direction, or maybe they've got shadows cast on them. But it turns out, in going through the data, there is one variable that overwhelms them all in terms of how much energy people save from this. And it's actually not surprising. It's exactly what you would expect. It's the amount of hot water that the household uses in the first place, because that determines how much energy they're spending in the first place on heating water. And therefore, since the solar water heater provides a fraction of that, then their savings go up if they use more hot water. Or it's not a good way to put it that way. If a household happens to use more hot water and they get a solar water heater, they're going to save more energy compared with a household that never used so much hot water in the first place. Not a good reason to use more hot water, because obviously the household that didn't use so much hot water in the first place was never spending the energy to begin with. But from the point of view, so that all is fairly obvious, and you can think it through, but what I wanted to do was see, what does the data show? So what's the actual performance? And so what I did was I drew out individual systems, and again, this one's preliminary so far because it's actually quite a laborious process to draw out each individual system and calculate their energy savings as a function of their annual hot water consumption. Hot water consumption is something we also measured. And what you see is no surprise. It's exactly what you would expect. The more water is used in a household, and it gets a solar water heater, essentially the greater the total savings, because they're a fraction of the total energy consumption. What I find interesting about it is that this one variable, how much hot water you use, really is almost the sole determinant of the energy savings. You see some spread, like this is a very strong relationship, and I put a best fit polynomial curve to it. It has quite a high correlation of 0.87. Essentially what it tells you is, if you didn't know anything else, but you knew how much hot water the home used per year, you could just about calculate how much energy they're going to save using the solar water heater, which is exactly what you would expect. But where's the differences? So here, there's quite a range here between this one and this one. So I checked those two, And remember all those other variables, right? Like how much it's sloped. Different slopes of collectors should get a different amount of solar radiation, different orientations, north, south, well, north's not a good choice, west, south, east. So I checked, this one is facing 50 degrees off of south and is at a very low angle. So there's a good explanation for why that one is pretty below the curve. And this one, which is really among the highest for its water use, that one is at a 45-degree angle and facing 16 degrees off of south. So, you know, the differences off this curve are mostly, or what I found so far, are mostly explainable. Now, what I'm going to do with this is continue laboriously, or maybe get one of my team to do it, going through the rest of them and getting all the rest of them up here to see if the curve stays the same. Okay. What I thought about it is, if you had this relationship and you could measure how much hot water a household was using, you could tell them in advance, you just do the calculation, how much they're going to save, more accurately than we currently are generally. So that would be a good tool for people in deciding about investing in a solar water heater. Was there, yeah, I think.
Just a quick question, Mike.
Sure.
Can you comment on the constant? So the 250, which we would assume, normally it's a direct relationship between consumption and kilowatt hours.
Yeah. So this constant here?
Yeah, where it crosses the axis.
Basically should be zero.
Right.
Yeah, and this was, well, I don't know if it's a real result. I mean, if you use zero water, then you kind of only have zero savings. So it might be just an artifact of the data. In fact, I was tempted to reset this so that it just forced the intercept to be zero, which might be a better approach. Yeah.
And was there any capturing of what their water use, hot water was used in advance, and putting the number of panels sort of correlating to that use, or did everybody get the same number of panels? So
good question. I was not involved in this assessments up front and the conversations with the customers about getting a solar water heater. So I don't know how much measurement was made of the water heating or the hot water consumption. I know most 99% of homes don't measure their hot water consumption. So that's an interesting thing. So maybe we should be, for various reasons, measuring the hot water consumption in really every home. But these, for this chart, are all the same size of system. They're all two-panel systems. I sort of factored that variable out. In the set, there are some one-panel systems, so I'm going to go back and do the one-panel systems separately. Okay, I'm told I only have a few minutes left, so I'll move on to solar electricity. And I'm not going to say that much about solar electricity because I only have 2 minutes left. But so in some ways, solar electricity is a little bit simpler to analyze. And that's because when you make solar electricity at a grid-connected building like this, if you have a net metering agreement with Nova Scotia Power, you essentially get credit for all of it that you produce. So you don't have this issue of, did I use up the solar energy? Because you can send it over the grid to someone else to use. That's an incredible benefit. So as a result, it's fairly simple to basically, and this is data thanks to Solar Nova Scotia. What I was involved in a study essentially where we got the real production data of solar electricity from 31 different systems around the province, 31 solar PV systems averaging in size of about 7 kilowatts at people's homes. And what this represents is the distribution of how many kilowatt hours they were producing per year per kilowatt of installed capacity. So it's normalized to per kilowatt. It takes about 4 normal-sized solar PV panels to make a kilowatt, so just to give you a sense of that. And the average fell right in between, well, 1150 was the average. But what I find interesting, well, the first thing I would say is, if you know nothing else, and someone asks you, if I put up a kilowatt of solar PV panels in Nova Scotia, what am I going to get for it? 1150. on average, because it's a reasonable average. And it doesn't vary. The other thing, it only varies by less than 10% across the entire province, right, from Cape Breton down to the south. The South Shore is a little higher, but it's still within 10% range. But what I most found interesting is that this was all 31 systems. So I love to look at the range. So some small number of people, got a system that was only making 800. So you'd want to go back and say, well, okay, what, is that one got shade on it? Are they facing a different way? But what I found most interesting is there were folks who were able to, with kind of optimal siting and orientation, get between 1,200 and 1,300. I think 1,284 was the highest one. So it gives you kind of an upper limit. And it tells you a couple things. Like if someone comes to you claiming that they're going to get 1,400 or 1,500, you might want to back check their calculation, right? Take it with a grain of salt. Now these are just for fixed systems. If they put it on a tracker, they could get that much. So it gives you a ballpark of what you should expect for energy value for a solar photovoltaic system. And just in closing, about our next project. So with the support of the province of Nova Scotia and ACOA, we are in our lab starting what we call our community solar data project. And the goal of that is to bring into a single database the production, the near real time, or at least at 5-minute interval, hopefully, production of solar electricity systems around the province. And then to make that database available for research purposes, for researchers, for example, Dalhousie University is a partner in the project. We're hoping that some grad students and postdocs will dig into this solar data and start to find patterns in it. And we hope to have a kind of public-facing part of it that would show you either now or today or yesterday how much solar electricity was produced in various parts of the province, what our solar power, if you imagine that there are soon going to be thousands of solar electricity installations in Nova Scotia. So if you imagine that they were all one big distributed power plant, what is that power plant producing, how is it behaving, is what we want to characterize. And we've made a start. We're only scraping the data from HRM Solar City right now, so thanks to them. HRM has started making its solar PV production data available on its open data platform. So we're starting by scraping that, but we want to go across the province and gather as input from as many solar PV installations as we can. And build a map where essentially you pick a time and date and it would show you how much solar was produced in each area. And then to get into forecasting, because that's the next thing is, what's tomorrow's solar electricity generation going to be, which could be very important for planning the utility assets for the following day. So that's what we're currently working on. And hope to be, well, it's a 2-year project to start that's just gotten underway a month ago. Dane George, who's right there, is leading that project. And I think I'm probably out of time, so I'll say thank you to everyone for coming.